Okay, I'm going to do a couple of factor change with gravitational field strength. Remember, this is the strength of the gravitational field for a mass that's above the surface or on the surface of a body. Our equation for that is G equals G times M. M is the mass of our object, like the Earth, for example, divided by r squared, where r is the radius of that object. Okay. And this is the equation we can use if we put in the mass and the radius of Earth and that gravitational constant. We end up getting 9.8. This is the strength of our gravitational field near Earth's surface. It's also the same value as our acceleration due to gravity of that gravitational field, or that acceleration that it's causing. Okay. Because we're not using big G, we're going to just do factor change here. So, what is the gravitational field strength at a point 1 Earth radius above the surface? Okay, so we've got 1 radius to get to the surface, and then we're asking about another radius above that. Okay, so we'll just do a factor change here. We're not going to worry about the constant G because that's, just a constant. We're going to say 1 for our mass because we're not changing that. And then instead of R here, we're going to have 2R, and we got to square that, right? Because it's squared in the equation. So that means that the gravitational field strength at a point that's another Earth radius above the surface is going to be 1/4 that of what it is on the Earth. So we could even get a number for that. I mean, it would be 1/4 of 9.8, which would be, about 2.45. So that G decreases as you get farther away from your planet or whatever body you're talking about here. We're mainly talking about Earth, but in gravitation we've been talking about other things too. So 1/4 would be the gravitational field strength once you're another full Earth radius out from Earth. So what if we were 2 Earth radii above the surface? So now we're not changing any mass, so I'm going to leave that as 1. But now I'm going to have 1 plus 2 plus 3 radii. So that's 3r. And again, that's squared. Remember, you got to square that. So now we're going to be 1/9 as great. So we would be almost down to, whoops, that's my phone, not my calculator. 1/9 is 0.111111. I'll multiply that by 9.8. That gives me an acceleration due to gravity of about 1 meter per second per second. So dropping off. Okay. Okay. And then let's look at another one. So here we've got the mass of a planet is 1/10 that of the Earth, but its radius is 1/2 that of the Earth. And what do we think the acceleration due to gravity is going to be? So this is one where we would use a factor of change, and then we would apply it to our Earth value. So I'm just going to write down here because I'm kind of running out of space. Okay. So we've got G equals 1/10 for our mass. And we're going to divide that by 1/2, and we've got to square that for the radius. Okay. So that's 1/10 divided by 1/4. And I'm going to flip this fraction up. So I'm going to have 4/10. Okay. So my acceleration due to gravity on this planet is 4/10 what it is on Earth. So I can figure that out by multiplying 4. Well, let's see. Let's do 4 divided by 10 is 0.4 times 9.8 is about right at 4 meters per second per second. on that planet. Okay. So we'll put 4/10 times 9.8 equals 4 meters per second per second. This one's kind of similar to one I did in class where we had planet Z, I think it was, and it had a mass and a radius that we compared to Earth, and then we figured out what the acceleration due to gravity would be there. So you figure out your factor here, and then you're multiplying that factor by our actual 9.8 to compare it. Okay. A big point of this is that as you get farther away from the planet or other body, the value of G decreases. And we saw that in this example here with our Earth orbits increasing. Okay. Okay, so that's just a couple of quick examples with gravitational field strength doing the factor of change.